All right, welcome to the Chapter 8.1 notes. We're going to be looking today at differential equations, which we've worked a little bit with so far this year. We're going to work on the language with it, formalize some things. We will continue to work on this on the next section as well. And we're going to introduce something new called slope fields. It's kind of a cool idea that we'll be pursuing. So first of all, I want to make sure you understand the directions. You'll have problems like this quite often where you're asked to find a general solution, and that's all they're going to tell you. And what you need to understand is that if you're finding a general solution, is you need to integrate to find the original function, which since this is dy over dx, this would be to find y. And since it says it's a general solution, you're going to have a plus c at the end. So anytime it says general solution, you're going to have a plus c. There are going to be times where they ask you to find a particular solution where they'll give you an ordered pair so you could figure out what c is. But when you're asked to find a general solution, that's going to have the plus c. Of the DE here, this is a notation can be used to shortcut differential equation. A differential equation is an equation with a derivative in it. So an equation has an equal sign, but it will also have a derivative in the equation. So you'll see the notation for a derivative in the equation. You might even have a first derivative and a second derivative. Some people call the differential equations diff EQ. There's whole college courses that people will shorten up and call diff EQ if you ever hear someone talk about that. So if I'm starting off with dy over dx, so I know what the derivative of some function is. I can find the solution to find out what y is by doing the integral of both sides. Now, something interesting to think about that maybe you've not thought about before, we tend to forget that this notation dy over dx it's like a division. Okay, this is like a division notation. What we can do is we can multiply both sides by dx and rewrite this as the integral of dy is equal to the integral of e to the x over 1 plus e to the x dx. So we can multiply both sides by dx and it ends up moving over on this side. This will become helpful with something we're going to do next class. It's not super critical that we do this right now. Well, the integral of dy is the integral of 1 dy, which is y. There is like a plus c here. We tend to not write it. We tend to write it over on the other side of the equation. If you wanted to write a plus c here, that's optional. I'll show you where it goes in a minute. On this left side, I'm going to actually use some u substitution to help with this problem. I'm going to let u equal the denominator. The reason I chose that is because the derivative of that is the numerator, is e to the x dx. So I can replace e to the x dx with du, and then I have 1 over u that I need to integrate. So when I integrate that right-hand side, here I had y plus c. This would be the natural log of the absolute value of u plus c. Now these two constants don't cancel out. We could think of it as they each have their own constant, which if you subtract from one side and bring it over, they combine to have a new constant. That constant could be 0. And that's typically why we don't put the constant on the left-hand side. We just recognize that it's going to move over to the right-hand side. And then remember, u is really 1 plus e to the x. And since e to the x is always positive, and when you add 1 to something that's always positive, you end up with a solution that's also going to be positive. I don't need the absolute values here around my argument. In fact, I should change them to parentheses. So why don't you guys try number 2. When you think you are done with number 2, you can unpause the video and compare. So again, these directions mean that I need to integrate. So I'm going to integrate both sides. I will then have the integral of dy. I'm going to move the dx over to the other side is equal to the integral of x times the square root of 5 minus x dx. I am going to use u substitution. There is a function within the function. And du is then equal to negative dx. It's easy to miss that negative. And this is a little problematic. Let me just do the left-hand side. When I integrate the left-hand side, I just get y. Remember, the plus c I'll deal with on the right-hand side. If I try to do some substituting here, I can replace dx with negative du. I can replace this 5 minus x with u. to the power of 1/2. But I can't just ignore this x. I can't just pretend it's not there. I also cannot move it outside of the integral. Only a constant multiplier can be moved out front. But what I could do is I could take this equation and reorganize it a little bit so that x is isolated. And I could say x, let me move x over to the other side and then move u over to the other side. X is equal to 5 minus u. Now the reason that that's helpful is because although the original expression here could not be simplified, this one can. I can distribute. This is going to allow me to use the power rule as I'm integrating this. This would be 5u to the 1/2 minus u to the 3/2 du. And I can use the power rule then on this left-hand expression. Now all of this negative, all of this is still going to be a negative. So u to the 3/2, I'll multiply by the reciprocal of that and get 10/3. Minus, let's see, this would be u to the 5/2. I'll multiply by the reciprocal. And then there is a plus c here at the end. Now, if I want, I could go ahead and distribute that negative. And I must rewrite this in terms of x. This is an indefinite integral. I cannot leave this in terms of u. I'm going to change this to a plus here as I distribute this negative. And remember that u has now been replaced with 5 minus x. So a little bit tougher integration. So we can still use u substitution, and you should look for it a fair amount. All right, on the next page, we're going to have an ordered pair. Normally, we would do this activity in class. Due to COVID and everything else, it doesn't translate very well to be done as much of an in-class activity. I'm going to do my very best to kind of walk you through what this exploration would look like. What would happen is you would have each received a piece of paper like this. It's in your notes packet. And we're dealing with this differential equation. It's a differential equation because there's a derivative in the equation. We want to find the slope of a tangent line for some ordered pair that we would be given. Well, the slope of the tangent line is dy over dx. So I could give you any ordered pair that would show up on this graph. And I'm just going to do maybe, we'll do a couple so that we can kind of get a general idea. Maybe we'll do the ordered pair 1, 2. Well, then according to my formula here for slope that I've highlighted in yellow, this would be 1/3 times whatever x is, which is 1 squared, which would be 1/3. And I could do this with a variety of ordered pairs. In fact, I'm going to. But I'm just going to sketch that slope. So what I'm going to do is I'm going to go to the ordered pair 1, 2. And I'm going to sketch what I think a slope of 1/3 would look like. Now, there is definitely some approximation going to happen here. This 1/3, let's see, I'm thinking it's looking something like that. I think that would be about up 1 over 3. Up 1 over 3. I'm just going to draw a little segment to represent what I think that would look like. Now, if we were doing this in class, each person would have their own ordered pair. Maybe the next person would have 1, 3. And what you might notice is, since this equation's in terms of x, they would still plug in a 1. And at 1, 3, I'd still get that same slope of 1/3. In fact, every ordered pair that uses an input of 1 would have a slope of 1/3. You could try that. You could plug in a couple points, but all of those would have a slope of 1/3. If I try another point, maybe I'll do the ordered pair 2, 0. Then my input here would be 2. And if I square that and then divide by 3, I'd get a slope of 4/3. So at the point 2, 0, I have a slope of 4/3, which would mean up 4 and over 3. And I want to try to model what that slope would look like, up 4 and over 3. I'm thinking something like that. Now, if I changed my output, it doesn't matter. I'm still going to get the slope of 4/3 because this derivative only uses the variable x. So I'm going to go ahead and continue to have that slope of 4/3 no matter which point I'm using, as long as x is 2. So that I'd get that same thing if I had 2, 2 or 2, 3 or 2, -1. Each of them would have that same slope of 4/3. If I pick a different input, maybe 3, maybe I'll do like 3, 4. Because I would need to plug in a 3 for x in my formula for slope, I'd get 3 squared, which is 9, divided by 3, which is 3. So the 0.34 is right here. I would do a slope that's like up 3 and over 1. That's pretty steep. That's steeper than my other ones. It is rather challenging. People get really nervous, like, how do I know exactly how steep it is? Yeah, no one's going to really judge you too much on that. And notice that all of those along that X would have that same slope. I'm creating what's called a slope field. Let's say I took a different input. Maybe I had inputs of 0, like the 0.0, -2. Again, if I use this formula for slope, I would just want to take my input and square it, and then multiply by 1/3, and I'd get 0. So I would have slopes of 0. Now, a slope of 0 is just horizontal. So no matter if it was 0, 1, or 0, 4, or 0, -2, I still am going to get, these slopes of 0. Going to work a little bit on my left side of this slope field. If I use inputs such as -1, so maybe I have the ordered pair -1, 3. It doesn't matter really what y is. My equation for slope only has an x, my differential equation. When I square -1, I get a +1, and I get a slope of 3 once I multiply that by 1/3. Well, that's the exact same slope, by the way, as I had earlier for a +1, and that's because when you end up squaring x, it didn't matter if my input was positive or negative. I'm going to get the exact same answer. In fact, if I plug in a -2 with whatever output I want, I will, like I did before, still get 4/3, like I did before. Up 4/3 to the best of my ability, challenging all of my lack of artistic ability. And if I plug in a -3, I'll get whatever output I want. For the derivative, I would still get 3, just like I did before. I'm going to just change these to a different color so that we can hopefully see the patterns. Up 3/1 is super, super steep, starting to approach a vertical. Now, I could do more points if I wanted. I could put 4 in, etc. But I want you to understand that this is a slope field. What this is this is a collection of tiny little segments that each represent the slope or the derivative at an instant. And so that's what that is. Now, if I want to find the general solution, you might remember from the previous page that when we're talking about a general solution, we're talking about working backwards to find the original function y. So I'm going to integrate both sides here. So the integral of dy would be the integral of 1/3 x squared dx. I just multiplied the dx to the other side. The integral of dy is y is equal to, I'm going to use a power rule. This one was nice, no use substitution, x cubed plus 3. Now we know what cubics look like, right? Like we know what x cubed functions look like. They look like this in general. But what we have is we have this plus c, which is kind of an interesting idea. And this will hopefully help you understand what that plus c means visually. What we're going to do is we're going to sketch this general solution on my slope field here, going through the ordered pair 0, -3. So I'll color this kind of this light blue. Starting at 0, -3, I'm going to sketch what an x cubed curve would look like. And what I'm hoping that you're seeing is that the path of my slope field follows the path of x cubed. What this x cubed plus c actually means is that I have a whole bunch. I'm going to color some things and then erase them in a minute. I have a whole bunch of cubics that could have a variety of constants that just shift them up vertically or down vertically. But they're all x cubes, and you might notice they all fit the pattern of the slope field. Let me get rid of those really fast, because I only want the one that we requested that goes through the ordered pair 0, -3. Now we want to write the equation of the particular solution, and what that means is this is telling you to figure out what c is, and then write y as a more particular, as a explicit or specific solution. So remember, y is equal to x squared plus x cubed, maybe, plus c, and I have this ordered pair 0, -3. which 0 is an x value and negative 3 is a y value. I'm going to put the negative 3 in the y value position and the 0 in the x position. And when I solve that, c is negative 3. And so my equation is y is equal to x cubed minus 3. And that's actually the equation of this blue curve that I drew. And I also want you to know that that blue curve can be modeled by the path, the direction of all the slopes in the slope field. You can almost think of this like a connect the dot. So on these next ones, you're going to have an opportunity to practice this a bit. So first one for number 4, draw a slope field for that differential equation. So maybe pause the video and give that a shot. When you're ready, you can restart that video. Okay, so what I'm going to do is I'm going to go ahead and just create some ordered pairs. It looks like I'm going like x's from negative 3 to 3, and same thing with y. So I could pick any ordered pair I want. Maybe I'll start with like the ordered pair like 0, 1. Well, notice this is in terms of y. So when at the point 0, 1, I would have a slope of 2 times 1, which is 2. So I want a slope that looks like it's going up 2 over 1. Now, if I pick another point with the same y value, like 1, 1, because I'm just plugging in a 1, I'm still going to get that slope of 2 all the way along this horizontal, because this is in terms of y. So when the y values are the same, I'm going to get the same slope. If I change what my y values are, it technically doesn't even matter what my x's are. I would then get a slope of 2 times 2, which is 4, which is steeper. Very steep. Hard to, once I start getting really steep, like just good luck. As long as I can tell they're uphill and steep, we're going to be happy. If I start using heights of 0, regardless of what the x coordinate is, but if the output is 0, I'm using 0 in my formula for slope, this would be 2 times 0. So I will get a whole bunch of horizontal segments for this slope field all the way across here. If I use a point like 3, negative 1, where the y value is negative 1, the slope would be 2 times negative 1. I'd like you to notice I'm using a 0 or an arrow, not an equals. I'm correlating an ordered pair to a slope. These aren't equal. I'm just using it to help identify what I'm using. And so I'd have a slope of negative 1. This would be downhill. Or negative 2. Downhill, a little bit steep. All the way across, because these are all in terms of y for my formula for slope. If I use something like 0, negative 2, it is in terms of y, plug in a y, I will get a slope of negative 4. A very steep slope in the negative direction. And so forth. If I had used y values that are 3, 2 times 3 is 6, like almost vertical. And same thing down here, would have slopes of negative 6, almost vertical but slightly negative. For number 5, interesting slope field, because you'll notice that my differential equation, my formula for slope, has both x's and y's. So maybe pause the video and you can try this one on your own. Well, if I have an ordered pair where x is negative 3 and y is 3, I'd have negative 3 over 3 with one more negative, and I would get negative 3 divided by 3. I'd get 1. And that's kind of how I'm going to fill these out. Now notice that there is a sign change here from the negative, but I'm going to do x divided by y with the sign change. And then here I'll do, again, x divided by y, but with the sign change. Positive 3/2, positive 1, positive 1/2, 0, negative 1/2, negative 1, and negative 3/2. And we could fill out all of these slopes. Now this table is just one way to keep track of all of your slopes. It's up to you whether you want to use that or not. If I put in a 3 here, then what I would get is I'd get negative 3 divided by 1 with another negative. So this would be 2, 1, 0, negative 1, negative 2, negative 3. Now, each of these numbers are slopes. So as I start drawing in my slope field, I need to be careful here because as I'm drawing them in, I want to make sure that I'm understanding what I'm drawing. So like at the point -3, 3, I'm drawing in a slope of 1, supposedly. At the slope of -2, 3, or at the ordered pair -2, 3, I'm drawing in a slope of 2/3, which is a little less slanted than 1/3. Now it's flat, horizontal. Now I'm in the negative direction, but not very steep, a little steeper in the negative. And then -1's like at a 45-degree angle. That was my first row. My second row, as I kind of draw these, so I've got +3/2, a little steeper than a 45, rise of 1/1, +1/2, 0, -1/2, -1, -3/2. And then if I do 3, or at the point, let's see, -3, 1 would have a slope of 3. That's pretty steep. Then a slope of 2, a little less steep, slope of 1, slope of 0, -1, -2, -3. And it is, like I said, hard sometimes to differentiate. Just do your best. Now, this part right here is really interesting, and I wanted to make sure and point this out to you. For this next part, I'm going to be dividing by 0. So I have like -3 divided by 0 times another negative. This is undefined. The way you would show an undefined slope on a slope field is a vertical slope. This is perfectly vertical. It's undefined. Every once in a while, you might even see times where people just leave that part blank. Okay, so you could see it done that way as well, but this is a vertical slope. If we finish the rest of this table, I would get +3, 2, let's see, these would be negative, sorry, -3, -2, -1, 0, 1, 2, and 3. I really am getting the same thing as the rows above. I just have a sign change. And sometimes once you start to see some patterns, that can help you fill out. Now, do you have to use a table? Nah, it's up to you. Okay, if you would rather just kind of calculate it as you go, there's nothing wrong with that, but I'm going to start drawing these in. So -3, -2, -1, 0, +2, or +1, +2, +3, and so forth. And then we can get our diagram. This is our slope field. Now, by the way, we would need a little bit more calculus to be able to solve this differential equation. But what ends up happening here is after a lesson next class, what we would find out is that the solution here for this differential equation is actually x squared plus y squared equals c squared. Depending on what constant I'm doing, we could think of this as a circle. This is like x squared plus y squared equals r squared, a radius. And if you kind of connect the dots, you might see there's a whole bunch of circles in this picture. So out of the 3 examples that we've done where we've had to draw slope fields, we've had one, the first one that we did, where all of the variables were only in terms of x, and they were always the same along a vertical. We've also had some where all of the variables in the differential equation were just y, and they were all the same along horizontal. And we also had some where it had both x's and y's, and you might notice they're all different. And so I'm going to pause the video right here, and we will continue on the next video.